Well, welcome back to our lesson on circular functions today. In this lesson, we're going to be working on finding the coordinates of points that are on the unit circle, and then also finding exact values of the trig functions of angles. So far we've already talked about and we've learned about finding exact values of trig functions, and we found that those exact values repeat in each quadrant. Some of them have the same sign, some of them have opposite signs depending on the quadrant that they're in. And we also found things like the sine of 30 is equal to the sine of 150. It has the exact same sign where they both are equal to 1/2. So in this lesson we're going to be discovering how these trig functions are going to help us find the coordinates of points that are actually on the unit circle. Let's look at an angle theta in standard position where we have the initial side along the x-axis, the positive x-axis, and the terminal side as shown. And that terminal side is going to intersect our unit circle at some point P, and it's going to have coordinates x and y. Okay, it's going to have an x and a y coordinate. Well, we already know that the sine of this angle from SOHCAHTOA and from our definitions of our trig function, sine is opposite over hypotenuse, so it's y over r. And the cosine is the adjacent over the hypotenuse, so that one is x over r. But r is equal to 1. And so we can just say if r is going to equal 1, then the sine of theta is just y and the cosine of theta is just x. Well, what did we just show? We just showed that every point on that unit circle can be written just as the cosine theta and then the sine theta, where the x-coordinate is the cosine theta and the y-coordinate is the sine of theta. We call these two trig functions circular functions because we define them using a unit circle. So when you hear the word or the term circular functions, we are talking specifically about the sine and cosine of theta. So let's look at some examples. If we have an angle in standard position, we're going to call it theta, and we're given the fact that that point has coordinates 2 square roots of 2 over 3 and -1/3. And they're telling us it lies on the terminal side on the unit circle. Find the sine theta and cosine theta. Well, this is almost too easy. The first coordinate is equal to the cosine of theta. The second coordinate, the y-coordinate, is the sine of theta. So sine of theta is -1/3 and cosine of theta is 2 square roots of 2 over 3. It's just that easy, for real. Now you have, let's go back to your unit circle. I have already had you find all of the angles in degrees and in radians, but we have all of these ordered pairs out here that we have not yet filled in. So now you are ready to fill those in. Okay, and we know that the sine of 30 is 1/2 and the cosine of 30 is the square root of 3 over 2. So the coordinates of that point are square root of 3 over 2, comma 1/2. And then the sine of 45 is root 2 over 2. Cosine of 45 is root 2 over 2. So there's the coordinates of 45. 60 degrees will be just the opposite as 30, right? So the cosine is 1/2, but the sine is square root of 3 over 2. And then your quadrantal angles. We know that the sine function starts at 0. So the y-coordinate here will be 0, but the cosine function, which is the x-coordinate, starts at 1. So this is 1, 0. And that makes sense, right? If we're at this point, its coordinate is 1, 0. The other quadrantal over here will be -1, 0. What about up at the top? That one's going to be 0, 1. And down at 270 degrees, we should have 0, -1. Now I'm going to leave it up to you to get the correct signs to fill in the rest of your unit circle. So please do that and bring that to class tomorrow. So the unit circle coordinates, we can plot those independently with the angle, where we put the angle on the x-axis, theta, in degrees or in radians, and then whatever those trig values are, square root 2 over 2 as a decimal. I think it's 0.707. Plotting each of those trig values on the y-axis, and we get these graphs. Well, surprise, surprise. I know I've shown this to you in a video where we plotted these sine and cosine waves based on the unit circle. So that is what we end up with. So go ahead and sketch those in. These functions are called periodic functions. The sine and cosine functions are periodic functions because they repeat, okay? Every 360 degrees or every 2 pi radians, you notice we start at 1 here and we start at 1 again, and it repeats at 360 degrees. The same for the sine wave. It starts at 0 and then repeats at 0 at 360 degrees. So algebraically, we can represent this by saying the cosine of whatever the angle is plus 360 is the same as the cosine of the angle. In radians, we would say the cosine of x plus 2 pi equals cosine x. Likewise for the sine function, x plus 360 and x plus 2 pi. So those two formulas algebraically in the last slide will help us to solve these problems here. It says find the exact values of the functions, and we've already been doing this. So really what we're doing is applying that formula that I just gave you. The cosine of 675 is the same as the cosine of 360 plus 315. If you subtract 360 from 675, we end up with 315. So that's just the cosine of 315. Well, now we need to figure out what the cosine of 315 is, and that gives us a 45-degree reference angle, and we're down in quadrant 4. So the cosine of 45 would be the square root of 2 over 2, and it's positive because we are in quadrant 4. So there's our exact value. Remember, when we're doing exact values, we're always going to have one of those 9 values from our chart or our table that we memorize, or we're going to have the 0, 1, or undefined for our quadrantals. How about the sine of negative 5 pi over 6? Remember, anything over 6 is going to be a 30-degree reference angle. So this one, if we just add 2 pi to it, we end up with the sine of 7 pi over 6. Remember, this would be 12 pi over 6, and 12 minus 5 is 7. So now what quadrant is this in? 6 pi over 6 is 180 degrees. So this is going to put us down a little bit further into quadrant 3. And the sine of 30 degrees is 1/2, but it's negative in quadrant 3. So we're down to our last slide. This one has a word problem about a Ferris wheel. So as you ride a Ferris wheel, the height that you are above the ground varies periodically as a function of time. Consider the height of the center of the wheel to be the starting point, and a particular wheel has a diameter of 38 feet. Remember, that's the diameter, and it travels at a rate of 4 revolutions per minute. What's the period of the function? The period wants to know how far do you go, how many seconds does it take you to go 1 revolution? Okay, time for 1 revolution. Okay, that's what you're trying to find. So if we want to find the period of the function, we know it goes 4 revolutions in 1 minute or 60 seconds. So we're just going to take 60 divided by 4, and that gives us 15 seconds. So it takes us 15 seconds to go 1 revolution. Then it wants us to make a graph where the horizontal axis represents time, the vertical axis represents height in feet. So if you just were to think about this, if this is time 0 and we go up and we're plotting our values on an XY chart, we're just going to have our sine wave. Okay? The only difference is this one completes a complete revolution, a complete cycle every 15 seconds. So your time, every 15 seconds, you're going to have another revolution. So after 60 seconds, you should go through 4 repeated sine waves. That'll do it for this lesson. We'll see you next time.